Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 54 of our electrical machines subject. So today we will discuss about power input of synchronous motor. Okay. So previously we discussed about the what do you call the power input to synchronous generator. So today we will discuss about power input to synchronous motors and assignment 20 as well. Many questions we will solve. Okay. So let's first discuss the expression, right? Let's derive few values. Let's first discuss the expression. So what is the expression for power input, right? So power input to the motor will be what? It will be basically, let me first write the apparent power input. Apparent power input to the motor SIM will be not VT, it will be E angle delta into IA conjugate. Okay, IA will be some vector quantity. What will be IA? So this equation we will use, right? I know my VT will be equals to E EF or E plus IA ZS. IA plus ZS. Okay, so what I can say is this is my value, right? So what is my IA? Remember what will be your IA? IA, this remember E is also phasor. VT is V angle 0 minus E angle delta divided by ZS angle theta s. Okay, magnitude of ZS angle theta s, right? So now I will replace my, what is my IA conjugate? So my IA conjugate V angle 0 degree minus E angle minus delta divided by magnitude of ZS minus theta s. Okay, so now I can derive the values, right? So I will replace my IA conjugate here. Okay, so from here I will get my apparent power input to the motor, that will be E angle delta, so will be multiplied with this, right? So it will be E V of angle delta minus E square, delta delta will get cancelled. I am just simplifying the calculation over here, divided by, like this will be magnitude of ZS divided by minus theta s. This will be magnitude of ZS divided by minus theta s. Okay, so SIM is equals to E into V theta s plus delta minus E square magnitude of ZS theta s, right? So this will be the expression for the apparent power. So what will be the active power, right? I want to understand what is the uh, active power basically. So Okay, okay, one mistake I have made actually. This is not the input to the motor, right? This is the input to the oh, sorry. This is the apparent power output of the motor. I'm sorry, I'm extremely sorry. This is the power at this point, right? At this point, what is the power? That is E into delta into IA star. That is the power at this point. This is the power output of the motor, because from the motor I will get some power. Now you might have a doubt, sir. You might have a doubt, sir. How am I getting apparent power output of the motor if it's like motor can drive active load, right? So of course motor needs reactive power for generation of flux. Okay, so the reactive power component or the imaginary component of this apparent power is the component required for supplying the reactive power, right? I will explain. Sorry, I'm really sorry. So this, right, this power is power at this point, apparent power at this point. That means it is the power output of the motor, and here I'm giving the power input from the terminals, right? So because motor has a impedance ZS, impedance ZS, right? So I have to observe how much power I am sending. Okay, I'm really sorry. So this was the SOM actually. Sorry. This will be SOM. I will derive the expression for SOM as well. Don't worry. Okay, let me keep it for at a side right now. Let me first find out the SIM. That is more important. So what is SIM? SIM will be, I'm really sorry, SIM will be VT into VT into I conjugate. VT into IA conjugate. Okay, so this will be equals to VT into IA conjugate will be equals to VT is V angle 0, IA conjugate this value only, right? So it will be V square divided by magnitude of ZS angle theta is minus EV by ZS angle of theta is minus delta. Okay, so from here I can directly write what is the active power and what is the what okay, why is this not coming here? Still it is not coming. That's weird. It will not go. Okay, I will send this one on that side. What is the active power input and the reactive power input from the load terminals, right? So active power input to the motor will be, this will be V square by magnitude, like just the cosine, right? Cos theta is minus EV magnitude of ZS cos of the real part. So theta is minus delta. Okay, so now if I assume one thing, that if I say that my RA is much smaller than XS, right, then that means my theta S will be approximately 90 degrees, right? So my cos theta S will be 0, right? So this will go to 0. Okay, so this will become minus EV by ZS cos of 90 minus delta. Now what is cos of 90 minus delta? So cos is here and sine is here, correct? This is sine, this is cos. So cos 90 minus delta is simply sine delta, right? Cos 90 minus theta is sine theta. So this will be minus EV by magnitude of ZS sine delta. Now you might have a doubt, sir, negative is coming. How can power be negative? So power, right? I'm sending from the infinite grid to the motor. So power has to be positive, right? Power input to the motor has to be positive. If it has to be positive, that means minus EV by magnitude of ZS sine delta has to be greater than 0. That means sine delta, because all other quantity are positive, so sine delta has to be negative. That means delta has to be negative. That means my E lacks V. From here I can directly prove it. Directly I can prove it. Okay. So now I hope you understand why we say that our uh, terminal volt, I mean the excitation voltage must lag the terminal voltage. Okay. I hope it is clear why it should lag. It is derived here. Many places you will see sometimes they write the angle as minus delta. Somewhere I also may have written here minus delta, right? So what that does is that keeps the formula same. That keeps the formula same. But I don't want you to just mug up the formula. I want you to understand the concept. Okay, I want you to understand the concept. So what you do, you remember the formula for the synchronous generator. Okay, you remember the formula for the synchronous generator. Again it is coming. I don't know what is happening. Remember the formula for the synchronous generator. Remember formula for synchronous generator. Only two, very simple. This active power formula only you remember, right? Other things no need to remember. For synchronous generator, and then replace delta to minus delta. Okay, remember the formula for synchronous generator and then replace delta to minus delta. That's it. Okay, replace delta to minus delta and you're good to go. You are good to go. Okay, so yeah, similarly you can of course derive the expression. So this is the general expression. This is the general expression. Okay, reactive power expression also you can easily derive, right? What will be the reactive power expression? Reactive power QIM will be equals to Vs V square by magnitude of Zs sine theta s, and it will be minus E V by magnitude of Zs by sine theta s minus delta. Okay, now I want to do one thing. I want to write what will be my POM, right? What will be POM? So POM, if I now write POM, again I have to add in a page, and again this will not let me add the page. This will not, this bug, man, this. Okay, so POM, right here I have pasted. Yeah, POM, what will be POM? POM, if I see, that is the power output of the motor. What will be the power output of the motor? It will be EV by magnitude of Zs into cos of theta s plus delta. How is it? It should not be delta right here. Or should it be delta? Okay, it should be delta. Okay, okay, yeah, it should be delta only. And it will be E square by magnitude of Zs into cos of theta s. And what will be the reactive power? Reactive power will be the same thing, just it will be replaced with sine. Okay, now few things I want you to notice. Again let's do the same analysis. Again let me say Ra is much lower. Ra is much lower than the synchronous reactance. Then that means my theta s will roughly be 90 degrees. Okay, theta s will be roughly be 90 degrees. So I can say, now what will this be replaced to? This will be replaced, right? This will be replaced with POM EV by Zs into cos theta is plus 90. So theta is 90, 90 plus delta, 90 plus delta is minus of sine delta. Okay, and remember delta itself is negative. Delta itself is negative. Remember that. Minus e square. Oh, this is anyway 0, right? Cos 90 is 0. So this is gone. So same expression I'm getting, right? Whatever power I was supplying, I'm receiving the same power. How is it possible? Because we made the RA to be 0. So there is no losses in the line. No losses are there in the line, right? RA is 0. So if there are no losses in the line, that means whatever power I'm sending from the infinite grid, it is the synchronous generator is totally able to convert it and send it to the load. That is the any mechanical load, right? It is able to send it, right? If I make RA to be 0, makes sense, makes total sense. Okay. What about the reactive power expression? So reactive power expression, you will see it will just be the opposite of the input of the reactive power. You will see. I will show you. So if I here, right, if I again RA is made 0, what will be the reactive power? What will the reactive power become? So reactive power will become V square by Zs. So theta is 90. So this will be V square by Zs, and if theta is 90, sin 90 minus theta is sin theta. Sorry, cos theta. So it will be minus EV. So this will not be Zs anymore. Xs, right? Xs cos theta. Sin 90 minus theta is cos delta. Okay. So what about here? So this will be Xs only, right? This will be Xs only. What about here? What will be QAM here? If RA is made 0, so it is again theta is 90. 90 plus theta. 90 plus theta is minus of sin theta. So it will be EV by XS minus. So minus already have written at the front. 90 plus theta is minus of sin theta. Correct? 90 plus theta is minus of sin theta. How can you remember it? So this is my cos, right? Let's say this is my cos theta and this is my sin theta. So if I am adding 90, I will be here. So it is what? It is minus of theta, minus sin theta. So that's why it is minus of sin delta. Okay, this is how I used to remember. This I have taught in my network theory. Okay. Okay. Now, this will be minus, and as it is 90, cos theta is 90, this will go to 0, right? Sorry, this, okay, sorry, this will be, sorry, what am I doing? This is sine, right? What am I doing? This is sine theta is, okay. So sine 90 plus theta, sine 90 plus theta will be cos theta only. Sorry, this will be plus cos theta only. This will be cos delta. And this sine 9 will be minus e square by Zs. So basically sine by xs, right? Basically sine 90 plus theta, if I am adding 90, right, it is simply cos theta. That's why sine 90 plus theta will be cos delta only. Okay, this will be e square by x square because sine 90 is 1. If I see over here, it is v square by x square, it is e square by x square. This thing is negative. This thing. So what is the difference between, basically? So what is happening? You might say, sir, it is not exactly coming negative. Why it is not coming negative? Because some of the reactive power is getting lost here in the synchronous reactance. Some of the reactive power is getting lost here in the synchronous reactance. Okay, because synchronous reactance has only reactance, right? Resistance has been gone. So whatever is the difference, that is QIM minus in whatever input I am giving, reactive power input I am giving, and whatever reactive power output I am getting. What is the difference? Difference is v square by x square minus v square by x square. This is minus only, right? Yeah, this is correct. Yeah, v square by x plus e square by x. So this is the amount of reactive power that is getting lost in the synchronous reactance. Am I correct over here? Just quickly want to cross verify this. Yeah, EV cos delta will get cancelled. Minus e square by x square will be remaining here. Yes. So bit of it, this much will be lost here. Okay, this much amount of reactive power will be lost here. So I hope it is clear everything is clear according to this. So you don't have to worry that much. Okay, just mainly this formula is the most important one. Okay, whichever one I have, okay, I did not box mark it. This one is the most important one. Okay, this formula, that's it. Anything else you can ignore it. Anything else can be simply ignored. Okay, this formula is the most important one. Reactive power you can always derive. It will not take you much time to derive the reactive power. So now let's do the same thing, that is same analysis as we did for the synchronous generator. So here, right, if I say that if the power is constant, that the power or the load across the synchronous generator is a constant load, constant load, then what will happen? Then what will happen? Then what will be constant? So first of all, this will be constant, right? That P equals to Vt Ia cos of theta. Okay, power factor angle. This will be constant. Okay, with respect to the infinite bus, right? I'm talking about with respect to the infinite bus. So where is the, yeah, this is the infinite bus, right? With respect to the infinite bus, I'm talking about the power. Okay, what else? So again, if I assume Ra to be 0, power will be E into Vt by xs into sine delta, and remember it was minus of sine delta, so I can put the minus delta inside. Okay, so if power is constant, then xs is a constant value, V is a constant value, excitation E sine delta also has to be constant basically. So basically E into sine of minus delta has to be constant. Okay, E into sine of minus delta has to be constant. So two things has to be constant here also. If P is constant, Vt is constant, then Ia cos theta also will be constant. Same thing, right? Same thing as we did for the generator, same thing is happening. So here Ia cos theta will be constant. So here it is theta 1, here it is theta 2. Okay, and here Ia3 theta 3 if it is leading, right? But this length will be constant. So basically what is happening, if I'm varying, basically what I'm talking about, if I'm varying my Ia3 Ia2, so if you see here, right, I'm increasing my Ia1. If I'm increasing my Ia1, right, length of Ia1, right, is increasing. Ia1 is increasing. If I am increasing the Ia1, what is happening? The theta is also increasing. Okay, theta is also increasing. If I am increasing Ia, theta is also increasing, which is reducing the cos theta. So with increase in Ia, theta is increasing, right? One more thing, if you remember about the excitation. Okay, so initially, if I say the motor is under excited meaning the motor does not have enough flux. That means it is operating in lagging power factor. The supply has to deliver the reactive power. So initially, if it is under excited, that means if motor is under excited, it is operating in lagging power factor. If it is operating in lagging power factor, that means my Ia maximum will be here, somewhere here. Slowly it will come to leading. So when the motor is under excited, we say it is lagging power factor, and we say that, yeah, same thing, that my Ia will start from here on the right hand side. Okay, and it will go to left. So we will start from left to right, we'll go from left to right. Okay, same we can discuss for this, right? E sine delta. Okay, here E sine delta has to be constant. So initially, if it is under excited, if the uh, if I say that the motor is under excited, that means EF value will be very low, right, then sine delta has to be very high because EF sine delta has to be constant, right? So EF value will be lowest. So if I draw, this is my VT, right? This is my VT. Let's say this is my VT. Okay, and this is my EF, right? EF will always lag VT, and the most important factor to note here is that EF sine delta will be constant. So this is the delta angle, right? Sine delta will be constant. Sine delta meaning this is the projection along VT, and this will be the projection perpendicular to VT. So this length, let's assume that this is my EF sine delta. This length, let's assume, okay, let me draw a line, perpendicular line here. EF sine delta, okay. So this value will be constant. So initially, if EF is very low, right, so delta will be highest, that is it will be almost 90, right? It will be almost 90, right? So EF magnitude is lower, but as delta is very high, hence the power will still be constant. Okay, I mean power will be still be the same value. So as I am increasing my excitation, that is, as this is, let's say, EF2, and I have here EF1. Okay, so as I'm increasing my excitation, you see the length of the EF vector is increasing and the delta is reducing actually. Okay, as we can see from the like equation as well, like nothing new I'm telling here. Also you can see that if I increase my EF, the delta will reduce. Okay, because this has to be a constant term, this product has to be a constant term. Okay, so yeah, that is the thing basically. So let's come to conclusions. What is the conclusion? Conclusion is, if my excitation is 0, that means the induction, that means the synchronous machine is operating in lagging power factor. As I will increase my excitation from lagging, slowly the power factor will increase because the flux, right, flux inside it is increasing, so the power factor will improve. So the power factor will improve, that means your theta will reduce. Okay, if the theta reduces, IA current will, sorry, theta will, yeah, theta initially was very high, theta reduces. So if your theta reduces, your IA current also reduces. Okay, initially your IA current also reduces. Then what happens? This is always constant, I'm increasing the excitation. Then what happens? Then if I keep on increasing the excitation, at certain stage your theta will go to 0, that is at unity power factor. As soon as it reaches unity power factor, then it is at nominal excitation, nominal. Okay, neither lagging nor leading. Then after nominal, what will happen? After nominal, again if I excite it more, so I'm providing extra flux, more flux intake. So that means it has extra flux now, so it will go to leading power factor, leading power factor, leading power factor, right? So it goes to leading power factor. That means in leading power factor, what happens? Again, if I see on the left hand side, the theta is increasing, so is the current. Theta is increasing, so is the current also is increasing, right? So initially theta decreases, current also decreases. Then after it reaches unity power factor, theta increases, current also increases. But remember, if theta is reducing, that means your cos theta is actually increasing. And here, if your theta is increasing, that means your cos theta actually is reducing. That is the important portion. That is the only important part, right? So basically, if I want to plot the graph with respect to excitation, what I see that if EF is here, right, and at certain excitation, right, some excitation, the the armature current, so the armature current will be very high, because it will be directly almost anti-parallel, it will keep on increasing, right? So if theta is 90, right, it will be very high length, IA current will be very high. You see that IA current is only increasing. So if theta is almost 90, IA current will be very high, it will be asymptote, something like this, right? Something like this. Again, IA current will reduce. If we see, IA current is reducing. It will reduce till a minima. This point will be the point of the unity power factor, that is nominal excitation, right? This will be nominal excitation. This will be under excitation, and then again after this nominal excitation part, it will keep on increasing. That is over excitation. Okay, and here, right, current will increase. If you see, current is increasing after reaching nominal excitation. And for the power factor, what will happen? For the power factor with respect to EF, right, basically the this is actually IF excitation. IF is proportional to EF only. Okay, the power factor will just be opposite, it will be inverted V curve. Initially it will be lagging, it will be leading after nominal excitation, okay, after unity power factor. And remember, it is just the opposite of generator. In generator, first leading came, then lagging came. Okay, opposite meaning just leading, lagging will be interchange, that's it. Okay, everything else will actually remain same. You can go and check. Okay, so now let's discuss about basically one more thing, right, for multiple powers basically. So if I say that, let's say this graph is for P1, right, and P1 is at, I'm talking about unity power factor. At unity power factor, nominal excitation, okay, nominal excitation, keeping excitation same. What will be P1? P1 will be V into IA1 cos theta, and cos theta is 1. Okay, now if I have another graph that is P2, and P2 is higher than P1, right, and if I say that it is also, it has to also operate in nominal excitation, right, then what can I comment about IA2? IA2 will be higher than IA1. So what do I understand? I understand that the armature current will be higher than the previous armature current if the active power is increasing. So the graph, right, will look somewhat like this. Okay, if the initial graph was this, okay, then the like this graph is for P1, this graph is for P2. Okay, this graph is for P1, this graph is for P2. Why? Because for the same amount of excitation, I will have to provide more current. Okay, so the graph will shift top right. So as I will increase my power, graph will just shift top right for the armature current. What about for the power factor? What will happen for the power factor? So for the power factor, right, if you see that, what will happen to the power factor, right? Okay, this is my cos theta. If I want to keep my, because now, okay, this was for the armature current. For armature, for power factor, how can I understand? So I am in, power is what? Power is V into IA cos theta, right? So if I'm increasing my power, you are saying IA will increase at nominal excitation. Okay, I agree with you. So IA will increase at nominal excitation. Okay, so graph will shift rightward. So to provide, so what is happening? So in the same excitation point, I see the how is the point starts. So it starts from initially lagging, then leading. So I see this is the now the nominal excitation point has been shifted on the right hand side. So I need to provide extra excitation to reach the nominal excitation for the P2 graph, right? So now previously for the same IF current, I am in the lagging zone rather being in the nominal zone. So if I see in the P1 graph, I am in the nominal zone, but in the P2, I am in the lagging. So basically, the graph for the cos phi, it is something like this, right? For P1, but this is the lagging. But if I increase my power, the graph will just shift rightwards. This will be P2, and this will be P3. Okay, P1, P2, P3. So graph will just shift rightwards. So these are the graphs basically. These are the V curves and the inverted V curves. And if I keep on increasing the power, then the power graphs will be just like this, and here it will just shift on the right hand side. Okay, like there is one more way to explain. I will explain in with a question. Don't worry, I will explain with a question. Okay, so like whatever we had discussed, the same thing is written over here. Okay, just like I discussed, right? Under excited motor will act as a inductor because it is under excited, it does not have enough flux in it, so I have to provide the flux. If it is over excited, then the synchronous motor will deliver the flux. Okay, it will not behave as a inductive load. Okay, uh, so here, right, the motor consumes the reactive power. Here the motor will deliver the reactive power if it is operating in overexcitation. Okay, so power factor will be leading. Why? Because load is delivering reactive power. That's why the power factor will be leading, and it is unity if it is a normal what is it, normal excitation. Okay, so that's why there is a very wide use case of synchronous motor. We use it to develop a leading load. So we will overexcite our machine by providing more field current so that it is operating in leading load, so that it is able to deliver the inductive load, right? Deliver the reactive power to the inductive load. Same thing is written over here. Synchronous condensers are known as the motor that are used as reactive compensator. Okay, it behaves as a controllable capacitor because I can control the how much reactive power I can supply with the help of field current. Unlike static capacitors, its output can be finely adjusted by regulating the DC current. It contributes to power factor correction. Voltage support and stability improvement in transmission networks. It contributes to power factor correction, voltage support and stability improvement in transmission networks. Why it's preferred? It's preferred. Unlike capacitor banks, synchronous condensers do not amplify harmonics. Okay, so yeah, capacitor banks, right, they are constant static supply. So basically their Q, how much reactive power they are able to supply, is fixed, right? But here the Q is not fixed. It can supply any amount of reactive power. Okay, and they have inertia which contributes to grid stability during transient. So this you will understand in power systems. You can neglect this one. Okay, so these are the key advantage of a synchronous condensers. Not that important for gate point of view. For EC point of view, you can go through this. Okay, let's solve few questions. Through this we will understand whatever we have discussed. A three-phase synchronous motor connected to AC mains is running at full load. Okay, it is operating at full load and at unity power factor. So it is operating at unity power factor and full load. So P is full load and cos phi is unity power factor. Okay, if its shaft load is reduced to half, so its shaft load is reduced to half. That means P full load by 2 with the field current held constant. So EF is constant. EF is constant. The new power factor will be what? What will happen to the new power factor? So this, right, you can understand it like this. If previously what was the power factor? Power factor is nothing but P1 upon S1, right? Previously cos phi S1, cos phi 1, right? So S1 is the apparent power, basically P1 plus JQ1. Now they are telling me that IF is constant, EF is constant. EF is constant, then roughly you can say Q1 will be constant, roughly. Okay, so your S2 roughly will be what? It will be P1 divided by 2, because it is consuming half of the active power, plus roughly JQ1. So now what will be the cos phi? Cos phi 2, cos phi 2 will be P1 divided by 2 S2, correct? Now what is S2 actually? If we see, S2 magnitude is lower, right? But will it be lower than this? That is what we have to identify. So as I have mentioned, right, if I am reducing the load, that means the graph will shift left. Okay, why it will shift left? So if you remember, if I was increasing the load, right, the graph was shifting on the right hand side. So this is P1, this is P2, correct? If you remember, P1, P2. So P2 was greater than P1. Okay. So this is my excitation, basically IF. This is my power. Okay. So yeah, now what can I say? Yeah, the same thing. If I'm reducing my power, basically I will shift leftwards. So previously, right, it was operating in nominal zone. So this was the nominal zone, right? If this is a nominal zone, graph will shift leftwards. So this will be my graph now. So in the same IF current I am observing, I'm getting what? I'm getting a leading power factor. Because initially it was lagging. Right now it will be a leading power factor. Okay. So I hope you're able to understand, because with equations we will not be able to solve it. That's why understanding the graphs is very important. Okay, with equations you will not be able to crack it. With equations you will not be able to crack it. Okay, again I will explain. So what we just decoded that if I increase my power, this is my excitation EF, and this is my power factor cos phi. If I increase my power, right, the graph will shift. If this was the graph for P1, graph will just shift on the right hand side. This will be the graph for P2. Okay, but if I'm reducing the load, so P2 is greater than P1, but if I'm reducing the load, basically I will go in the left hand side. If I'm reducing the load, I will go on the left hand side. Okay, so remember, always for a motor, initially we start with lagging, then we start with leading. Same for this graph as well, right? But they are telling me excitation is fixed. If excitation is fixed, then basically this is my initial excitation IF, right? This will be fixed. So this graph will cross it my drawing is bad. This graph will cross somewhere here, right? Somewhere here. So what is this region? This region is actually for P1. It is on the right hand side of the nominal excitation for P1. So which is leading, basically, So that's why the new power factor will be leading power factor. Okay, the new power factor will be a leading power factor. So let's solve the next question. This is the next question. A three-phase synchronous motor with constant excitation is connected to an infinite bus. Okay, So 3-phase synchronous motor with constant excitation. So EF is constant. Okay, so if EF is constant, that means basically my power PEF V by XS minus of sine delta is also constant only. It is also constant only. Okay. Uh, and is supplying a fixed load at leading power factor, and is supplying a fixed load at leading power. Fixed load meaning power is constant. So this value is constant. So my sine delta also has to be constant. Okay, because everything is constant. Excitation is constant, right? If the mechanical load on the shaft is reduced. So if the mechanical load on the shaft is reduced, that means if the power is reduced, what will happen? The torque angle decreases while the power factor becomes more leading. Torque angle will reduce, yeah, because if power is reducing, this is constant, so this has to reduce. If this has to reduce, delta has to reduce. Okay, don't get confused by the negative sign. Okay, delta has to reduce. Basically delta will be more closer towards Vt. Basically E will be more closer towards Vt. So delta will reduce, that is for sure. Delta will reduce. And what is happening if I'm reducing the power? What will happen to the power factor? So if I'm reducing the power, again I will go back to the power graph, right? If I'm reducing the power, right, this is my power factor graph cos theta. Let's say this was my p, right, p graph. Okay, if I reduce the power, that means the power graph shifts to the left hand side, and it was operating in some excitation. It was operating, I don't know in what excitation it was operating, just constant excitation they have mentioned. So let's assume that it was operating here, right, somewhere here. If it was operating somewhere here, what do I notice? Not exactly at the same place. Okay, this graph is, let me put this graph more here. So let's say this was operating somewhere here. Okay, if it was operating somewhere here, I see that for this p1 graph the power factor was 1. For this p2 graph, right, for same excitation, right, I am observing it is intersecting it somewhere down, right? So power factor has reduced. Basically power factor has reduced, so power factor will also reduce, cos theta will also reduce, because it is intersecting it here. So just to summarize, okay, just few things I tell you to remember. This one you can remember, that your power factor graph will shift right if active power input is increased. Right, this one I will tell you to remember. So power delta will reduce and cos theta also will reduce. So torque angle reduces, no, this will not become more leading, no. uh, Torque angle increases while power factor becomes less leading. So initially, right, okay, is it telling me it was already leading? Okay, it was operating at a leading power factor. So leading power factor is, okay, sorry, if it was operating at a leading power factor means it previously it was operating here. Okay, okay, let me not shift it that much, otherwise you will not be able to understand the difference. Okay, this is my p. Okay, p2. So it was operating leading, so this region is leading, right, over excitation, and this region is lagging. So it was operating here, so it will still be operating in the leading region only. It will be more leading actually. Why more leading? Because here the power factor was very good value, somewhere like 0.7, if I say 0.7, but here, right, it is some very low value, right? Here it is intersecting with the same excitation, it will be 0.2, so it will be more leading, power factor becomes more leading, right? So yeah, this one is actually correct, option E is correct. Okay, torque or power angle decreases, more leading. This one is also correct actually, both the torque and power factor reduces, this one is also correct. But can I comment, I cannot exactly comment that it will reduce only, I cannot, yeah, because if this graph shift right is more left, then if it is more closer, no, even if it is more closer, right, it will be leading only, yeah, it will be less, more leading, yeah. So this both options will be correct actually, that power factor will become more leading. Why more leading? Because it is going more towards zero power factor, right, more leading, and power factor will decrease. So both the options A and D are both are correct. Okay, A and D both are correct in this. Power factor will become more leading and power factor will reduce. Okay, let's now move on to the next question. So this graphical questions are easy if you are able to understand this concept, right? This is actually a bit important, so I'll tell you to remember this concept. Let's now solve few numericals. Basically, a 480 volt, okay, it's a 480 volt, Vt is this, right? 480 volt, what will be the per phase voltage? Per phase voltage will be 480 divided by root 3. F is by 60 hertz, P is 6 volt. Delta connected, okay, it is delta connected synchronous motor, delta connected synchronous motor, uh, which is rated at 400 horsepower at 0.8 lagging. Okay, so I can convert this into kilowatt, that I will do later. Synchronous reactance they have given me is 1.1. Machine is assumed to be lossless, so Ra is 0. Okay, determine the magnitude of the internal generated EMF. So what will be the magnitude of the internal generated EMF? It will be basically, it is a motor, right? It's a motor, very simple, right? So infinite bus is here, synchronous reactance is given, they are asking me the internal generated EMF. So it will be this 480, it is a delta, okay, it is, sorry, it is a delta connected. If it's a delta, right, I don't have to divide by root 3. Okay, just be careful what they have put. So it's a delta connected, so we don't have to reduce by root 3, so we can directly calculate the this 80. But they have actually, I don't know what is the armature current. How will I find out what is the armature current basically? So we have to find out armature current. How will I find out armature current? So it delivers 400 HP. Okay, here it has told me that it is delivering 400 horsepower, right? So this, right, you have to remember what is the conversion between horsepower and kilowatt. So if you remember, 1 horsepower is equals to 0.735 kilowatt. Okay, so it will be 4. So I have to first of all calculate the, so EF will be what? EF will be Vt minus J IA XA. What is IA? So one thing I know, root 3 into VL IL cos phi equals to power, right? 3 phase power. So it has already told me that it is delivering 400 HP of horsepower. Okay, if it is finding 400 HP of horsepower, so if I convert, like 1 HP is 0.735, so 400 HP will be 400 into 0.735 kilowatt. So this value will be 400 into 0.735, 294 kilowatt. Okay. So from here, I know what is cos phi. Cos phi is already told to me that it is 0.8 lagging power factor. So 294 10 cube divided by root 3 into for VL. VL is this, right? This is the line voltage only, 480 into cos phi is 0.8 only given to me, 0.8 lagging power factor. So this will be 294 into 10 cube divided by root 3 divided by 480 into 0.8. It comes out to be 442. So armature current, line current comes out to be 442. Remember this, right? This graph or this circuit is per phase equivalent. Per phase equivalent. So what is the phase current? Remember, what is the phase current? Phase current for delta will be this divided by root 3. Okay, don't make that same mistake. Phase current will be this divided by root 3. Okay, so 442.03 divided by root 3 will be the phase current. Angle is given to me, it is lagging 36.86. 0.8 power factor is 36.86. So divided by root 3, 255. 255.21 angle minus 36.86. Okay, now can you find out the excitation voltage? Definitely you can. Definitely you can find out the excitation voltage. What will be excitation voltage? It will be Vt minus IRA. So Vt is how much angle? It is 480 angle 0 minus Ia is this value 255.21 into minus 36.86 into JXA, right? J is 1 angle 90. Sorry, XS is I guess 0.8 or 1.1. Sorry, 1.1. Okay, so this will be into 1.1. So minus 280.73 angle. This will be 63.13 degrees 480. This will be equals to 280 into cos of 63 point not cos, okay, not 63, right? I think it is 56 point something, sorry, 53.13, my bad. So 280.73 into 53.13 cos of this, so it will be 168 plus 480, so it will be 301.56. And what about, because this negative sign is already, it was always there, and minus the reactive component, basically it is 53.13 sine into 280.73, so it is J 224.584. So this whole square plus 311.56 whole square whole under root, so it comes out to be 384. And what is the angle? I want to find out. So angle will be 224.584 divided by 311.56 tan inverse, and negative. Remember, it is negative because it is minus j, and it makes sense. It should come out to be negative only. Okay, it should come out to be negative only. Okay, so it will be minus 35.785 degrees. Okay, this will be your uh, delta basically. Okay, so yeah, I hope you have understood this point. Now if you want to prove it, right, you can prove it. So let me use that formula. P is equals to ef Vt by xs sine delta, sine of minus delta. Will it work? So ef we have just calculated 384, Vt we know that is 480, divided by xs. Xs is 1.1 into sine of delta, sine of minus, so it will become plus 35.785. So sine of this divided by 1.1 into 480 into 384, so it comes out to be something 97,000 something, right? Is it correct? It's kind of not correct. Okay, what is wrong? Okay, it is three phase. uh it is three phase power only. Okay, yeah. Oh, sorry, this side, this comes out to per phase. This is per phase power, right? So 384 into 480 divided by 1.1 into 35.785 divided by 1000. This is per phase power, right? Per phase, single phase. What about three phase power? Three phase power will be multiplied this by 3. So if I multiply this by 3, it comes out to be 3 phase comes out to be 294 kilowatt, which is exactly what we had actually initially thought of, right? That is the power. So I'm just doing the back calculation. This is just for the back calculation, that whatever we have derived is correct. Okay, remember, this is just the single phase power formula. Okay, so everything is per phase here. Okay, now next what they're asking, this is the part A basically. We have found the first part. The next part they are asking, find the maximum torque the motor is capable of producing. What is the maximum torque that the motor is capable of producing? So what is the formula for torque? Formula for torque is power upon speed, right? So what will be the maximum torque, right? What is speed? Speed is constant for a synchronous machine. It is omega s. Omega s is basically what it is. If you remember, what is ns? Ns is 120 f by p. So your omega s will be what? So if I want to write from here, right, what is my uh, omega s? So omega s, right, 2 pi ns by 60 is omega s. So this, right, if I multiply 2 pi by 60, this will become 4 pi f by 6, 4 pi f by p is equals to omega s. Okay, 4 pi f by p is equals to omega s. So we know the number of poles. We have already calculated here the number of poles. Frequency we know 60 hertz. Everything we know. So we just need to find out the we just need to put the values. So omega s will be 4 into pi into 60 divided by number of poles, that is 6. Number of poles is given to me, that is 6. Okay, so this will be 10. So 40 pi 40 into pi. So omega s, it comes out to be 200 and 125.6. Remember, here the power has to be three phase power. It must be three phase power and not single phase power, right? It must be three phase, because at the output, right, the load does not understand whether it is a three phase or single phase, right? The load is three phase power only, right? So we already know the three phase power, that is 294 kilowatts. So 294 into 10 raised to power 3 divided by omega s, that is 125.66, right? This will give me the maximum torque into 294. So 239.57 Newton meter. This will be the maximum torque. Now, why is it called maximum torque? Because this torque is not possible, right? Of course, there will be some friction and windage loss. All those things will be there, right? Due to that, I will not be able to get this much amount of uh, what do you call torque. I will not be able to get this much amount of torque. Okay, so this is the maximum torque that we will get basically. Okay, okay. So yeah, let me solve the part C. Part C is what? If the internal EMF is increased by 15%, calculate the resulting armature current. So if I increase the internal EMF by 15%, right? Okay, then what will be the armature current? Same thing, right? Same thing I can do. That I'm increasing the EMF by 15%. So EMF now becomes basically 1.115 times the previous one. Previously EMF was 384 magnitude. 384 times 384 times 1.15. So this, the new EMF becomes 441. And have they talked anything about the power? uh, if they have not talked anything about the power, right, so that means the power is constant. Power is constant, so power will be constant obviously. If power is constant, that basically means my EF sine delta will be equals to EF dash sine delta dash. So the new delta dash will be basically old EF. So okay, this will become 1 by 1.5 into the old sine delta. Old sine delta was this, right? 35.754. So it will be actually negative sign automatically will get cancelled. 35.754 785. Okay, so 35.785 divided by 1.15 0.508 sine delta. So from here I can easily find out my delta dash. Delta dash actually it will be negative. Please remember delta dash will be something negative. Okay, tan inverse, sorry, not tan inverse, tan sine inverse. Delta dash will be minus 30.56. Why it will be negative? Because of course it will be lagging. The internal EMF has to lag, it cannot lead, right? Otherwise current will come out weird value. So IA, right, will be what? IA vector, it will be basically VT minus EF dash angle, this delta dash, divided by the JXS. Very simple. So from here VT is 480, I guess. VT is 480 angle 0 minus EF dash. EF dash is EF dash is 380. EF dash, new EF dash is basically 441.5 6 angle, this will be negative 30.56 degree divided by j xs. So xs is 1.1 angle 90. So IA equals to, this is cos of this into 441.6 plus 480. So this will be 100, and this is negative, right? And already this is negative, so this will become plus actually. So 30.56 sine into 441.6, this will be plus j 224.53 1.1 angle 90. Okay, 100 tan inverse 60. To 24.53 whole square plus 100 whole square whole under root. So this will be 245.8 90. So your new armature current is 223.45 angle 24 degrees. Okay, so this will be your minus 24 actually. This will be minus 24. 90 is going upwards, so it will be minus 24. This is the phase current. What have they asked? Resulting. So this will be the phase current. Line current will be what? Line current will be root 3 times this, right? This is the phase, root 3 times this. So it will be 223.45 into root 3, so 387. Okay, 7, that is the magnitude amperes. What is the power factor, by the way? Power factor cos phi will be with respect to this angle. So cos of minus 24 cos, that will be 0.91, and of course it is lagging, right? Because the angle is negative over here, that's why it will be lagging. So I hope that portion is clear. Okay, this question is clear. I hope this question is clear. Mostly this you have to do the circuit analysis, that's it. You don't have to do anything else. Okay, so let's now solve the next question. A 3-phase 50 hertz star connected, okay, it is star, okay, very important information, it is star connected load cylindrical rotor machine is running as a motor. Okay, so it is a 3-phase 50 hertz star connected running as a motor operated from a 6.6 kV. So V per phase will be 6.6 kV divided by root 3. Okay, and draws current at unity power factor. Draws current at unity power factor. So IA bar will be IA magnitude into unity power factor, that is theta will be angle 0. The synchronous reactance of the motor XS is J30 ohms per phase. The load angle delta is 30 degrees, that is given to us. The power delivered to the motor in kilowatt. What will be the power delivered? It is very simple, right? It is simply per phase power will be what? Per phase power, single phase power will be EF Vt into Uh, is the armature current magnitude is given? No, armature current magnitude is not given. So ET EF VT by XS into sine of minus of delta. Okay, they have already given me that the load angle is 30. Actually, it is minus 30, but if they are telling you 30, that means basically they know that you know that it should lag. Okay, this much information you know. Okay, so what will be the power input to the motor? That is what they are asking. Okay, so uh, this we can, this formula we can use, right? Yes. So line is lossless. So EF, do I know about EF? Okay, I don't have any idea about EF. So okay, I cannot use this formula. Okay, I cannot use this formula. No, I cannot use this formula because I don't know what is EF. I don't know what is EF. That much I don't know, right? So what can I do? So few interesting thing again, you can take help of the phasor. So I know this thing, right? Your E angle delta is equals to Vt minus J IA XS. So if your V have they told us about the load is unit, it is operating in unity power factor. Okay, it is operating in unity power factor. If it is operating in unity power factor, okay, then it becomes quite easy. I just need to find out the IA current. Okay. So what I can say, if it is operating in unity power factor, right? Like there are many ways to solve this question, first of all. But one of the way can be this, that if it is working in unity power factor, I know this, right? That my IA current will be what? Vt minus EF angle of delta divided by J XS. Okay. So the numerator, right, can only have imaginary component, then only the J will get cancelled, then only IA will be totally real because IA is totally real because it is operating in unity power factor. So I can say that this EF, right, will have two components. One component will be EF cos delta, other component will be EF JEF sin delta, right? So basically I can say that the real component will be totally cancelled out, right? So basically I can say that Vt minus EF cos delta must be 0. Why it must be 0? Because the numerator and denominator both must be purely imaginary, so that Jj will get cancelled, so that Ia also comes out to be purely real. Even if there is slight real quantity, then totally the J term will not cancel. Okay, so that is why this has to be equal to 0. That is why I can say I know what is my cos delta, I know what is my Vt, so from here I can easily find out my EF. So EF will be Vt 6.6 kilovolt divided by root 3 divided by cos delta. So cos delta is 30 degree, right? So this will be 6.6 divided by root 3, cos 30 is 30 cos, right? 0.866 into 6.6 divided by root 3, 4.4 comes out to be 4.4 kilovolt. Okay, this is my E. So can I find out what is my I? I can find out what is my I, right? So now I know, if I write down this expression, what is my IA? IA will be, the real term is gone. Imaginary term will be minus EF sin delta. And remember, your delta is negative. That's why negative sign automatically will get cancelled. Okay. And there will be a J term, right? So that's why I was saying that this J and this J will get cancelled. The real term is already gone, 0. And only I will be left with this value. Basically, EF sin delta divided by XS. Okay. So I know what is my EF, that is 4.4 kilovolt. I know what is my sin delta. Sin delta is sin 30. Sin 30 is half. I know what is my XS, that is 30, I guess, right? 30 they have given, yeah, it is 30. So from here I can easily write, this will be kilowatts, kiloamps basically, not kilowatts, sorry. So this will be 2.2 by 3 into 100. Okay, this will be I. Okay, 2.2 divided by 3 into 100. Okay, so this is my IA current basically. Now I will put this value in the power because I need to find out the three phase power. What is three phase power? Three phase power is root 3 into VL into IL cos theta. It is operating in unity power factor, that's why cos theta is 1. VL I already know, that is 6.6 kV, right? 6.6 kV. Okay, so from here I can easily find out the power, root 3 into 6.3, 6.6 divided by 2.2 divided by 3 into 100 into cos phi is 1. So this will be 2.2. So this will be 2.2 whole square into root 3 into 100. So 838.31 kilowatt is my answer. Okay, this much amount of kilowatt it will send. So they have asked in kilowatt only, right? Kilowatt. So answer will be this 838.31. So before proceeding, I want to just quickly summarize one thing. This thing, right? That we discussed actually for generator. So this was for the motors, right? So I will just quickly summarize one thing here. Okay, before going starting with the next one. What do you need to remember for V curves and inverted V curves? Okay, summary, because that may be confusing to you. So this you just try to remember. Summary, let me draw here 4 graphs. So this is basically my for generator. Okay, this is for generator, and this is basically my excitation, and this is my current IA. Same thing I will draw for the power factor. For the power factor. Okay. So let's understand few things. One thing I know for certain, that the current diagram, initially we will start with some very low power factor, right? Zero power factor. I don't know whether it is leading or lagging. Okay. So starting point will be like, how to remember the graphs. Starting point is low power factor. That is for certain, either leading or lagging, right? Low power factor. Low power factor means cos theta will be very low. Now I know my power is constant. So if power is constant, that means my current IA will be very high. So I know the starting point IA will be very high. Okay, so I will start somewhere from here. Okay, starting point IA will be very high, and the ending point IA also will be very high. So the armature current will always be a V shape. So armature current will always be a V shape. Now the question will come whether on the left, this is the nominal excitation, right? The middle center, the lowest nominal excitation mean power factor is 1. So this point is the nominal excitation. This one will be the under excited, and this point is the over excited. Okay, so this point is the under excited, this point is the over excited, correct? So now what I can say is, what is this leading or lagging? That is what I want to do. So what does under excitation means? Under excitation basically means that the synchronous motor does not have enough flux, right? So it will take the flux from the load, right? So our synchronous generator is connected over here, and here I will have a load connected, right? I'm just showing you the isolated case. Here I have a load connected. So you're telling the synchronous generator is under excited. Under excited meaning it does not have enough flux, not enough flux. So what it will do, it will take the flux from the load, right? So load is delivering reactive power, so it will be leading. If you see here, right, it was just opposite. If I show you, it was just opposite. Okay, sorry, here, right, it was lagging, right? If you see here as well, in the graph, so this is lagging. Initially under excited, it was lagging, but here it is leading. Why? Because load is delivering reactive power. So I just wanted to clear the confusion, because I know there will be confusion. How will you remember the V curves? Okay, I'm just telling you a shortcut. So load is delivering reactive power, so this point will be leading, right? Because load is delivering. So again, power factor is always with respect to load. So as load is delivering reactive power, so the left hand side will be leading, and obviously the remaining side will be lagging. Same for the power factor graph, it will just be opposite, right? Because initially IA will be very high, then slowly power factor will improve because I'm increasing the excitation. So at nominal excitation, cos theta will be 1. So it will be highest and it will be inverted V curve. Okay. Now this was for a, let's say, power P1. Okay, again this point will be lead, this point will be lag. Now for other powers, let's say P2, let's say P1 is less than P2 is less than P3, what will happen? The power factor graph will just shift on the right hand side. That's it. This will be, let's say, P2, and this will be, let's say, P3. So power factor graph will just shift on the right hand side. If I increase the power, if I reduce, it will shift on the left hand side. That's it. That is what you have to keep in mind. Okay, same will happen over here, but it will shift on the top right. Okay, it will not just shift on the right hand side, because armature current also has to increase, because power has increased, because for nominal excitation more power, right? So what will happen, it will shift on the top right. Okay, so that's how the graphs will move. For generator, for motor, I have just discussed, right? This one will be lag, this one will be lead. Right hand side will be lead, left hand side will be lag. So that's how you remember. That's how you remember. How do you remember for a motor? Very simple, right? Again, initially I don't have enough excitation. If the motor, so I will draw the circuit diagram for motor. Graphs will be exactly same. Okay, I can actually totally copy this page, right? Just the circuit diagram will be different. So that's how you remember. So in the exam as well, you can draw this and you can remember how, what will exactly happen. So summary for motor. Okay, for motor, what will happen? This is the infinite bus, and this is my load. Actually, motor is the load itself. Motor is the load itself. Now I say it is under excited. Under excited meaning not enough flux. Not enough flux. So motor needs flux. Who will deliver the flux? Who will deliver the reactive power? The supply will deliver the reactive power. Q. Supply will deliver the reactive power. So this time it is receiving. That means the load is lagging. As it is receiving reactive power, load will be lagging power factor. So this time it will not be leading, it will be lagging. Everything else will be same, and this will be leading. Okay. So I hope this thing is clear, because I wanted to clear it. I know there will be a bit of confusion, so trust me, in PrepFusion there will not be any confusion at all. Okay, I do understand there can be a bit of confusion, so I have cleared that confusion as well. So let's now solve the next question, this question, right? So a three phase 11 kV 50 hertz. Okay, so star connected, so my V phase will be 11 kV by root 3 F equals to 50 hertz, pole equals to 2, synchronous motor connected to a 11 kilovolt 50 hertz source. Okay, fine. Its synchronous reactance XS is 50 ohms per phase, and its stator resistance is negligible, so Ra is 0. Okay, let me write this in different color. The motor has a constant field excitation, that means EF is constant, magnitude of EF is constant. At a particular load torque, its stator current is 100 amperes at unity power factor. So IA is 100 amperes, 100 angle 0. It is unity power factor. If the load torque is increased so that the stator current is 120, so now the IA dash is 120 amperes. I don't know what is the theta dash. Okay, then the load angle at this load will be, what will be the load angle that they are asking. Okay, so they have increased, if the load torque is increased, so the stator current is 120 degree 120 amperes now, so they are asking. Okay, if I use the initial excitation value, I can actually find out the value of EF, because I know what is IA, I know what is V, I know what is XS, right? So what will be EF equals to, so EF will be equals to VT minus J IA XS, right? So VT is 11 by root 3 into 10 cube minus 1 angle 90 into IA 100 angle 0 into XS. XS is 50, right? 50 ohms. So this will be right. If I calculate this value, 11 divided by root 3 into 10 cube, 6350.853 minus, this will be 50 into 100, 5000, J 5000, right? So my EF will be this whole square plus 6350.853 whole square whole under root. Okay, I have done some mistake. 5000 whole square plus 6350.853 whole square whole under root. Okay, it is not a mistake. 8082.9 angle. What is the angle? 5000. Again, you see delta is negative, right? 6350.850 tan inverse. So it will be minus 38.21. So this was the initial torque angle, but they are actually not asking this, right? They are not asking the initial torque angle. They are asking me that what will be the final torque angle, right? So magnitude of excitation will be same, current has changed. So again, if I put back in the same equation, that what will be current, IA will be equals to EF, sorry, VT minus EF angle, EF dash angle delta dash divided by JXS. So actually here I don't know what is my EF and VT, right? Torque, they have just told us that load torque is increased. Okay, okay, magnitude of current is 120. So can I somehow do something here? Magnitude of current is 120. So this will be, IA will be in vector format. VT is 11 by root 3 into 10 cube minus EF magnitude is same, right? Magnitude will be 8082.9 only, but delta dash I don't know what will be the delta dash, divided by J50. Okay, so this will be equals to 11 divided by root 3. This will have two components, minus 8082.9 cos of delta dash and minus J 8082.9 sine of delta dash. Okay, divide by J50. Now will this help me? Yes, this will help me actually. So if I take the magnitude on both sides, right? Take the magnitude on both sides. What will be the magnitude? So magnitude of IA is given to me, that is 120. Magnitude of the right hand side, this will be, so I will just put it like this only. V phase whole square, V phase minus E cos delta dash whole square plus E into sine delta dash whole square. Okay, and from here I can directly calculate the this right is yeah, sorry. So from here I can directly calculate the delta. How? Because I will have only one unknown left. I will have only one unknown left. Okay, so into 50 also is there, into 50, this whole under root, right? I'm just taking the magnitude I'm taking, so this square plus this square whole under root, and this is magnitude of this is 50 only, 50 goes here, 120. So I will square on both sides. So this will be basically 12 into 5, that is 60 into 100 whole square equals to V phase whole square minus E cos delta whole square, right? So this will be V phase whole square plus E square cos square delta square, and here also I have a E square sin square delta square, that will become E square only, minus 2 V phase into E phase into cos delta dash, and this term is automatically clubbed here, right, with cos square delta and sin square delta. So I can directly write what will be my 2 V phase into E phase, right? So basically my cos delta dash will be equals to, if I put it on the right hand side, it will be V phase whole square, basically V phase whole square plus E phase whole square, E whole square minus 6000 whole square. So what is V phase whole square? 6350.8 whole square plus E phase. E phase was 8082, right? 8082.9 whole square minus 6000 whole square. Then we divide by V phase into E phase. 2 into V phase, that is 6350.8 into E phase. E phase is 8082.9. 8082.9. So cos delta comes out to be 0.678. Remember, delta is negative, right? Delta has to be negative. Don't make delta to be positive. Okay, delta has to be negative. So here, if I do cos inverse, delta dash comes out to be 47.267. It is, if you just put here 47.267, it will be wrong. Okay, if you just put here 46.267, it will be wrong, and many educators in this field have put the same answer. Your delta has to be negative, it cannot be positive, right? For motor, delta has to be negative. So delta dash will be minus 47.267, right? Because cos of minus theta and theta are same. So just be careful regarding this. This is the answer. Negative sign will be the answer. Okay. So is there any easier way to solve this? That is what I'm trying to think. I think no, this is the most easier way. that we can think of actually. Is there an easier way? There is another easier way actually. Yeah, there is another easier way. That can I think of it? It is what I'm trying to think. Is there any other easier way? Cos delta, sin delta, et sin delta. Okay. So let me try with phasors once. So this was the method one with simply equations, right? Let me try once with phasors. Okay. Just for a second, let me give 1 second. This is the answer. We have got the answer. Minus 47.267. We have got the answer. I'm trying with phasor method 2. So I know the in the first case one, in the case one, basically I know my current was 100 angle 0. It was unity power factor. So this was my VT over here, right? IA current also was in the same direction because it is unity power factor. This is IA, and what will be like the EF will be basically VT minus J IA XS, right? So minus J IA XS. So if I rotate this in the clockwise anti-clockwise direction plus 90, this will be here, but I have to rotate in the anti-clockwise because it is minus J. So I have to subtract this from VT, right? So it will be along this direction, somewhere around here. Okay. So my E will be this. Okay. So this will be my EF. Okay. So this is my EF and this will be my initial delta. Can I find out this delta? What will be this delta? So this EF, right, will have two components. One will be along this line, another one will be perpendicular. So the EF cos delta, the projection of EF cos delta, right, will be just this length, right, this phasor, that is VT. And EF sin delta, right, this perpendicular component will be just this length, right? What is this length? IA into XS. So I can easily find out what is tan delta. That will be IA into XS. That is 50 into, sorry, IA is 100 into 50 divided by VT. Remember this is in per phase, right? So this is 6350. 6350. So this will come out to be 5000 divided by 6350 tan inverse. It comes out to be 38. Sorry, your delta comes out to be minus. Remember, it will be minus 38.219, right? 217. Same thing we had, I guess, derived over here as well. Okay, so we got the delta, we got the EF. EF will be what? So if I just replace here, right, EF, I will get my value of, if I replace here with cos delta, I will get my value of EF. So EF will be this times cos inverse into 6350 80 0.23. Okay, so now what I can do is, this is EF equals to 8082.23, right? So I got EF, I got delta. So in the next case, EF dash also will be Magnitude of EF dash will be same only, EF equals to EF only, that is 8082. But let me draw the phasor in the next case. In the next case actually they have not mentioned me. I don't know what is the direction of the theta. Theta I don't know whether it is lagging or leading. Okay, I don't know whether it is lagging or leading, because in the next case they are telling torque has increased, but whether the current will be lagging or leading, that I don't know. I don't know about that. Okay, so let me assume anything. So let me assume if I'm in, okay, one thing, they are telling that they are increasing the torque. They are increasing the torque, right? If the load torque is increased, that means the power deliver has to be increased. If the power deliver has to be increased, keeping the same excitation, what will happen? Do you remember it? Again the graph will come into the picture. Again the graph will come into the picture, right? So this is the graph, right, of power factor for a motor. We told that if the power is increased, right, this is my P1, this is my P2. If the power is increased, then the graph shifts on the right hand side. If the power is increased, then the graph shifts on the right hand side. So if the graph shifts on the right hand side, that means what? That basically means that initially for a motor, what is the case? Initially under excitation, so low flux, so it needs reactive power. So initially it will be lagging, right? It was at nominal excitation. It was at nominal excitation, but keeping the same excitation in P2 graph, because power has increased, so it will be in the lagging region only, because left hand side of the nominal excitation is lagging region only. So we don't need to assume, actually it will be lagging only. It will be lagging. Okay, so power factor will be lagging. We got the information. So this is hidden information, and trust me, this method no one will teach you. No one will teach you this method, right? Intuitive way. So power factor will be lagging only. Now let me draw the phasor diagram again. If I draw the phasor diagram again, this is Vt. Power factor is lagging, so my Ia will be somewhere around here, and this will be my theta dash. This will be my Ia dash. Okay, what will be your E, right? EF. So your EF will be again minus j. Minus j means rotate in the anti-clockwise direction, so minus 90 here into xs Ia dash into xs, right? So this will be my E. This will be my EF. Magnitude is same, but angle has changed to delta dash. So again if I, so this will be what? So this is theta. This is theta, and okay, if I extend this value, right, if I extend this here, this is theta, and okay, I want to understand what will be this value. Okay, this value is theta. If I extend this, right, just hold on, give me a second. So this value is theta dash, and this is 90, right? So this will be what? It is a triangle, so this will be 90 minus theta. This will be 90 minus theta, and if this is 90 minus theta, right, this will be what? This is 90, right? So this will be theta only. This will be theta. Okay, So from here I can, this will have two projections, right? One projection will be here. What will be this length? This length will be IA sine theta, and this much amount of length IA into xs, right? IA into xs sine theta, and this much amount of length will be IA into xs cos theta. Okay, so what will be my EF? EF also will have two projections along this line and perpendicular. So again I will write the same equation. Okay, you might think, sir, this is taking more time because I am explaining it to you, and this is you are doing first time. Okay, first time you are doing, that's why it is taking more time. So EF cos delta dash will be equals to Vt minus Ia xs cos theta. Now here, right, what is unknown? Cos delta is unknown, cos theta is unknown. So I don't know both of these values, so I cannot eliminate here, right? Now next equation, if I write that EF sin delta dash, this perpendicular component, will be equals to Ia into xs sin theta. Sin theta. Okay. So from here, can I do anything? I don't know what is theta. I don't know the power factor angle. Okay. So okay, we have to do the same thing only. That squaring and stuff, right? I guess. Because I know here I know I know xs, but I don't know what is theta. So theta dash, right? This is theta dash. I don't know what is theta dash. So if it xs sin delta. Okay. Okay, so do I know how much power has been increased? No, power how much? I don't know. Okay, anyways, okay, you have to do, like, basically what you have to do is you have to okay, one thing you can do, because I have to eliminate theta, right? Theta I don't know, so what I will do, EF cos delta minus Vt minus EF cos delta dash divided by Ixa equals to cos theta dash, and your sin theta dash equals to this divided by Ixa, and I will square and add them up, so I will get my answer as delta. Okay, this is complex. Delta will be minus 47.21. I do agree, because we are doing the same thing here again. Whatever we did here, right, to simplify, we did the same thing only. Okay, but there can be in other times where this will be simpler. Okay, here it is complex because you have to square and add. It is coming out to be same only, but sometimes it will be simpler. Okay, what have I done? So I don't know what is theta dash, so I just written here cos theta dash equals to this, and sin theta dash will be EF sin delta by Ixs. So I will take the square, right? So cos theta dash plus sin square theta dash will be 1. Cos square theta dash plus sin square theta dash will be 1. So that is eliminated. So only this much is left. Okay. So let's now solve the next question. Statement link question. A synchronous motor is connected to an infinite bus at 1.0 pu. Okay. Synchronous motor is connected to an infinite bus at 1.0 pu. Okay. So Vt is 1.0. So now they are discussing about per unit values. Vt is 1.0 pu. And voltage, and draws 0.6 pu current at unity power factor, right? So it is drawing 0.6 amount of current. So Ia is 0.6 pu at unity power factor. So theta is 0. Its synchronous reactance is 1 pu. Resistance is negligible. The excitation voltage and the load angle. It's very simple, right? So they are asking me excitation angle and load. So what is my P? P is Vt into Ia into cos theta, right? And remember, in per unit, it does not matter whether it is line or phase. Line and phase are same. In per unit, line and phase are same. Okay. So Vt into Ia into cos theta. So cos theta is 1. So power will be 1 into 0.6. That is 0.6 pu. I know the formula for power. It is equals to EF into Vt divided by xs into sine of minus delta, right, if resistance is negligible. So from here I can easily find out, okay, I don't know what is delta, I don't know what is Vt, okay, these things I don't know. Okay, so anyways I have to solve the equation only. Okay, I cannot use this equation, this equation is not enough, right? So we have another equation, right? So basically, again, if you draw the phasor, you will be able to easily solve it. Okay, if you draw the phasor, so your Vt will be here, your Ia is here, right? Your J Ixs will be here, so your E will be here, right? Again, E will have two components, right? So E cos delta will be equals to Vt, and your E sin delta will be equals to Ia. This length is what? Ia into Xs. So it will be Ia into Xs. So from here you can easily find out what is my tan delta. Tan delta, like, look, I am not, what I can do, I can remember the formula and directly write here tan delta, right, the formula, but I'm not doing it, I'm deriving it, because in the exam I also want you to derive only, in the exam I also want you to derive only, okay, because you will not be able to remember this formula. So Ia Xs divided by Vt. So Ia into Xs, Ia is 0.6 into Xs one divided by Vt. Vt is 1, right? Xs is how much? Xs is actually 1p. Okay, okay. So tan delta is 0.6. So remember, delta is negative. Delta is negative. Okay. So tan inverse 0.6 will be, delta will be minus 30.963. They are asking me what is the okay, what is the load angle delta? Delta will be minus 30.96 lag. It will be lag. It cannot be lead. Right? Lead is not possible. Right? It will be lag. So this will be answer. Okay. If you want to, you can obviously cross verify what will be the value of E. So I can put here in this equation, right? So value of E will be what? Vt by cos delta. So cos of this, right? Take the inverse. It comes out to be 1.17, which is absolutely correct, which is present here. Okay. So whatever we have calculated is correct. Now let's solve for the second one. Keeping the excitation voltage same, the load on the motor is increased such that the motor current increases by 20%. So load is increased. So again, if the load is increased, again the same graph, right? Same thing. This concept is very useful to you. So this you have to unfortunately remember. This is easy to remember, right? If load is increased, where will the graph shift? Graph will shift on the right hand side. Okay, this is the nominal. Previously this was my nominal excitation. Okay, and I know on the left hand side I will have always lagging, right? So previously this point was the nominal excitation for this graph P1. Now the load has increased to P2, so it is cutting it on the left hand side of the nominal excitation for the graph P2, so it is lagging. So now the load has become lagging, current will now be lagging. Okay, so current will be lagging now. So leading, what they are asking, the operating power factor. So leading is not possible, leading is not possible, so automatically two options are eliminated. Either option C or option A can be correct. Okay, so let us check. They are telling me the motor current has been increased to 20%. Motor current, excitation current has been increased to 20%. So I have to calculate the power factor. So how will I calculate the power factor? So we can use that equation, right? So EF equals to, keeping the excitation constant, EF is equals to Vt minus J Ia Xs, right? So this is now not unity power factor anymore, this is lagging, right? So from here we will have two equations, right? This will be EF angle, remember, minus delta dash. Okay, so this will have real component will be EF cos of delta dash will be equals to this Vt is real only. Now what is real here, over here? So this Ia, right, will have two components. Ia will have two components. Ia will have two components, that is Ia angle cos of theta plus IA j sin theta, right? One will be real, one will be imaginary. It is a phasor quantity. So if I replace it over here, so IA cos theta, so this will be imaginary term, j multiplied will become real. So j into j becomes minus 1 is already there. So this will become plus IA sin theta. Okay, so EF cos delta is equals to VT plus IA sin theta. What is EF sin delta? So without drawing phasor also I can solve it. EF sin delta. So I am telling you different methods, whichever one is suitable to you, you use that method. So EF sin delta will be this, right? Remember it is negative here. Okay, it is negative over here because it is EF of minus sin delta. Okay, it will be this component, right? IA into cos theta, this is real. I am multiplying minus j, so basically minus 1. So imaginary component will be equated with the imaginary component. So it will be minus IA cos theta. Okay. Now what I will do? I will do a very tricky thing. I will just square both sides and then add them too. If I add the two and square both sides, what will I get? Basically, I have to eliminate delta. I have to find out power factor, right? So if I square both sides, this will be EF square cos square delta square plus EF square sin square delta square, in which basically cos square delta plus sin square delta will be eliminated. This will be equals to VT plus IA sin theta whole square plus IA cos square theta, right? So from here I can easily find out this will become only EF square, right? EF square. I know what is the EF square because excitation has not changed, so EF square will be same only, and this will be equals to VT square. VT square is 1 only plus IA sin theta. IA, remember your current has increased to 20%, increased by 20%. So previously if it was 0.6, it will be 0.6 into 1.2. So 0.6 into 1.2, sorry, 0.6 into 1.2, so it will be 0.72. 0.72 into sine square theta plus 2 into 0.72, so not 0.7, sorry, 0.72 whole square, right? So this will become actually okay, let me keep it here, IA square into sine square theta plus 2 into 0.72, because IA is 0.72 now, into sine theta plus IA square cos square theta. So again sine square theta plus cos square theta will be 1. So ultimately I can write sine theta will be equals to EF square. EF square is 1.17 whole square minus 1 minus IA square. IA square is 0.72 whole square, that is 0.5184 divided by 2 into 0.72. Okay, just solving the equation. So minus 1 plus 1.17 whole square. Okay, it is coming out to be something negative. Theta is coming out to be something negative. Is this should be lagging, right? It cannot be negative. I'm doing something wrong. Okay, this right. Just give me 1 second. IA square VT is 1 only. EF is 1.17, right? So this will be IA square 2 plus, am I doing it correctly over here? It's correct only, minus J x's plus, okay, it becomes, what am I doing now? That is what I'm trying to think. Theta is coming out to be negative. It is lagging. If it is lagging, oh sorry, it is a lagging current, right? If it's a lagging current, basically it will be theta is negative. If theta is negative, automatically, yeah, okay, theta is negative. Oh, that is fine. Theta should be negative because it is lagging current. Okay, what I'm telling, it is correct only. Theta is negative, right? It's lagging current because it should lag the voltage. So theta should be come out to be negative only. Okay, I was doing correct only. I was just tense, man. What has happened? What happened, man? Okay, minus 1 minus 0.5184 divided by 2 into 0.72 tan inverse. Okay, so your theta comes out to be minus 5 point, not tan inverse, sorry, minus 0.103 sine inverse, yeah, 59, some, okay, from some minus 59 degrees. So your, what will be your cos, the cos of this, it will be cos theta will be, it is almost unity only, 0.994 lagging. Your theta is negative, right? Very important, your theta is negative because your current lags the voltage, that's why theta is negative. So whatever we have done is absolutely correct. Okay, so this will be answer 0.994. This will be the new power factor, 0.994 lag, which is present in the option A. So option A will be correct in this case. Okay, so let's now solve this question. Lot of questions we are solving. Okay, I guess 2 more questions are left. After that we are done basically. Okay, so let's solve this question. So a 2300 volt 3-phase synchronous motor is driving a pump and is equipped with line ammeter. Okay, so it's a sync 2.3 2300 volt synchronous motor is driving a pump and is equipped with a line ammeter and field rheostat. Okay, field rheostat. So we have a RF that will basically control the field excitation IF. The field rheostat is adjusted to minimize the AC line current. So tell me, we vary IF, and when is the AC current minimized in the armature? If you remember, it is minimized under nominal excitation. Okay, so the armature the ammeter shows 8.8 reading. So at nominal excitation, the ammeter current is 8.8 amperes. Okay, basically the armature current is 8.8 amperes. At nominal excitation, the armature current is 8.8 amperes. This much information I know, and I know what is the voltage. Voltage is 2300 volts. Okay, now what are they telling me? So they are telling me that calculate the power delivered to the pump assuming negligible losses. So what is the power delivered? Power delivered is simply V into IA cos theta, right? If it's a 3-phase power, right, it will be root 3 into IA cos theta. Okay, root 3 into IA cos theta. So let's assume that this, if nothing is mentioned, it is always assumed to be line voltage. Nothing is mentioned, it is always assumed to be line voltage, and already they are telling me this is the line ammeter. So line ammeter reads 8.8 ampere. So at this stage it is nominal excitation, that means my cos theta will be 1. So my power will be root 3 into VL. VL is 2300 volts into IA. IA is 8.8 into cos theta is 1. Okay, so 2300 into 8.8 into root 3. So it comes out to be 35 kilowatts. Okay, almost 35,056.7 kilowatts. Okay, so this is the power, that reactive power that it would be delivering. Okay, this much I know. Now what they're telling me, this is the first part of the answer. Determine the reactive power that the motor supplies if the system operates at 0.8 leading power factor. Okay, so system will operate at 0.8 leading power factor. Now if the system is operating at 0.8 leading power factor, right, so that means my cos theta is 0.8. Now one thing I know, that still it is operating at, like, it is still delivering power to the pump. So pump will still consume power, so power will be constant, right? Active power will be constant. Active power will be constant. If I am changing the excitation, the cos theta will change, active power will be constant. So if active power is constant, what is my active power? Equals to root 3 into VL into IA cos theta. This will be equals to root 3 into VL dash into IA dash into cos of theta dash. Okay, so what I can say is of automatically root 3 will get cancelled. VL dash is constant, that will not be staying here. So IA cos theta will be equals to IA dash cos theta dash. So IA cos theta cos theta dash. So I know what is my IA cos theta, right? So from here I can easily tell what is my IA dash because I know theta dash. So the new armature current I know. So what will be the new armature current? IA dash will be equals to, what was the previous armature current? It was 8.8 divided by the new power factor, that is 0.8, into the old power factor, that is 1. So it will be basically 10 amperes, right? 8.8 divided by 0.8 will be 11 amperes. Okay, so I have got my new armature current. So my Q will be equals to root 3 VL IL sin theta dash. Okay, so root 3 into VL is, I know what is my VL is 2300 into IL is 11 into sin theta dash, sin theta will be 0.6, right? So into 0.6 into 2300 into root 3 will be 292.53 VAR. Okay, and it is leading, right? So it will deliver the reactive power, not absorb. So this will be the answer. So in kVAR they are asking kVAR. So kVAR will be what? So Q will be 26.292 kVAR. Okay, remind the reactive power motor. So they remember, as they're telling motor supplies, so I don't have to add a negative sign. So already that is accounted for. Okay, so this will be positive only because that they already know, and we also know, if the motor is operating in leading power factor, that means it is delivering. So they have already told that motor will deliver only, so I don't have to add a extra negative sign. If they would have told that find reactive, this will be the answer. Okay, let me clear the confusion. This will be the answer. Find reactive power absorbed by the motor, then your answer will be minus 26.292. because why? Because we know that here it is operating in leading power factor, so it will deliver, not absorb. So the question has asked as opposite, so that's why an extra negative sign will be there to signify this, that it is delivering, not absorbing the power. Okay, very important. So mostly synchronous generator questions, right, will be covered with basics. Okay, you don't have to do anything, just equation, basic one equation. Okay, that one KVL equation, that is your whole chapter will be gone. Okay, let us solve the next one. This is the next question. A 3-phase 6 pole, so number of poles is 6 and it's a 2.3 kVA, so V line is 2300 volts and kVA is S rated is 200 kV, star connected. Okay, star connected, right? So it is star connected, so that means your V phase will be 2300 divided by root 3. Okay, V phase will be 2300 divided by root 3. Has a synchronous reactance of 12 ohm per phase, so its excess is 12 ohm, negligible armature resistance. So most cases your armature resistance will be negligible. Okay, it will be called 0 only, because to simplify calculation, otherwise questions will be very lengthy. Okay, now initially it operates at a load of 120 kilowatts. So it operates at a load of 120 kilowatts with a field current set such that the armature current is minimized. That means basically if the when is the armature current minimized? Again, your V curve is very very important, right? So field current and this is the armature current, it is minimized. Minimized meaning nominal excitation, right? So that meaning cos theta will be 1. Okay, so from here I can easily find out the armature current. What will be the armature current? So it is they have given, it operates at a load of 120 kilowatt, so it is given as the 3-phase power. So P is equals to root 3 VL IL cos theta. Cos theta is 1, so IL will be P, that is 120 into or IA, because in star line current and phase current are same. So 120 into 10 cube divided by root 3 into VL. VL is 2300. Okay, so this will be equals to basically 12000 divided by root 3 into 2300, so it comes out to be 3 amperes. Okay, approximately the armature current comes out to be 3. Am I correct here? I think no, 10 I am missing, right? 10 I am missing. So 30.12. That's why the armature current cannot be this low, right? 30.12. Okay, 30.12 amperes. Okay, so yeah, this is my armature current. Now what are they asking? Determine the, okay, now the field excitation is then increase, so IF is increased. So if IF is increased, what is this? Leading power factor, right? It has more flux now, leading power factor. So if IF is increased, it will be operating leading power factor, causing the armature current to rise by 50%. So obviously armature current also will rise here, as you can observe, right? So armature current has been risen to 50, increased by 50%, right? So IA dash will be 1.5 times the previous IA, so it will be into 1.5, so it is 45.19 amperes. Okay, at this new field setting the load is reduced to 60 kilowatt. At this new field setting the load is reduced to 60 kilowatt. Okay, so load will be reduced to 60 kilowatt, right? You say power has been reduced to 60 kilowatt. Previously the load was 120 kilowatt. Okay, determine the new armature current. What will be the new armature current that they are asking? Sorry, okay, causing the armature current to increase. Okay, determine the new armature current. So new armature current is very easy, right? New armature current is very easy because it will become 1.5. So this will be the first answer. New armature current is very easy. But what is the power factor? So power factor is again very easy, right? Power factor is again very easy. Power factor will be power will be equals to root 3 into VL into IL into cos theta, right? I know what is the power, I know what is the VL, I know what is the IL, right? I can easily find out the new power factor. So the new power factor cos theta dash will be P 60 into 10 cube root 3 into VL. VL is 2300. So new power factor into I also is there, right? I is 45.19. So into 2300 into root 3, this into 60 into 10,000 comes out to be 0.33. And what will it will be? It will be lead. So the new power factor will become 0.33 and it will be lead. Am I doing everything correctly over here? 2300 Let me check it. Cos theta root 3 VL cos phi, right? Power is 60. Yes. Yeah. Because power has been reduced to 60 kilowatt. So it is correct. Power has been reduced to 60 kilowatt. Okay. So yeah, I hope it is clear. I hope the question is clear to you, because they are what they are telling the new if I field excitation is increased causing the armature current to rise by 50%, at this new field setting the load is reduced to 60 kilowatt. Okay. Actually, the question is kind of okay. Sorry. So this question is kind of a trick question. Okay, I'm really sorry. Question is a very trick question. What do I mean by trick question? So they are telling me that they are increasing the excitation. Yeah, actually, sorry. This is wrong. This is wrong. So what they're telling me, first point, increase the excitation. So IA dash becomes 1.5 times of IA. Then secondly, what they're doing is reduce the load to here, right? Here the power is constant. Here the load is still constant, that is 120 kilowatt. Reduce the load to 60 kilowatt. Reduce the load to 60 kilowatt. That will basically reduce the load to 60 kilowatt. That will keeping EF constant. That is the important. Like, this question is actually very elegant. Here, what are they telling? So, at this new field setting, now we reduce the load to 60 kilowatt. So, I have to actually find out the EF. So, the information that I have to find out here is EF, right? EF, and that EF will be constant here. And here in this particular load, I have to find out IA and theta, cos theta. Very interesting question. Okay. IA double dash and cos theta dash, because then also power factor will change. If I reduce the load, then also power factor will change. Okay. So graphically, what is happening? Graphically, they are telling me that I'm increasing the excitation. Okay. If I'm increasing the excitation, I will be somewhere around here, right? In the leading zone. Now they're telling me they have reduced the power. So if they have reduced the power, right, somewhere the graph will come down, right, on the left hand side. Graph will come down on the left hand side. So still it will be in the leading zone only, but the armature current will reduce. Armature current will reduce. Okay, and of course the power factor also will change. So let us first do the first case. In the first case, everything will be same here, same calculation. This will not change actually. This is correct only. Here also this is correct, but this is IA dash. But I have to find out IA double dash and cos theta dash. So IA dash is correct only. IA dash is not wrong actually. So IA dash is correct, and this is also correct, cos theta dash. But remember, your power is constant here. Power is not 60. Power is 120 still. Power is not 60. Power is still 120. So this will be your cos theta dash will be power, that is 120 kilowatt divided by root 3 into VL. VL is 2300 into IL dash. IL dash is 45.19. So this will be the power factor. So 120 into 10 cube divided by root 3 into 2300 into 45.19. So it comes out to be cos theta dash comes out to be 0.66. Now I actually want to find out what is my EF. So what is my EF? So EF, right? I want to find out the excitation. EF angle minus delta will be Vt minus J Ia XS. Again, this will have two components, real and imaginary. So EF cos delta, because cos of minus delta and plus delta is same, will be Vt. Again, here it will be Ia plus, remember, plus Ia XA sin theta. This I have just done in the previous question. I will directly write it. Vt will be plus Ia XA sin theta. Okay. And your EF sin delta will be equals to directly minus of, because this is minus delta, right? Negative. But although okay, delta anyways will come out to be negative, that is fine. You don't write delta minus, because delta anyways will come out to be negative only. So this will be minus of Ia XS. So this is not XS, sorry, XS minus of Ia XS cos theta. Okay. So I can easily take out the ratio of these two to find out the delta. So tan of delta will come out to be minus of Ia, this is Ia dash, right? Ia dash. This is sin theta dash. So tan delta will be minus of Ia dash. Ia dash, Ia is this, right? 45.19. 45.19 into XS. XS is XS is, I guess, what was the value of XS? 12. So it is 12, and your XS is 12 divided by cos theta dash is also there, right? Cos theta dash. So cos theta dash will be 0.666, and this will be Vt. Vt is how much? Vt is 2300 divided by root 3, right? So 2300 divided by root 3 plus 12 into, sorry, 45.19 into 12 into sine of theta dash. So this is cos inverse into sine. So this will be 0.7454. Okay. So tan delta, so this value, right, if I want to calculate this into 12 into 45.19 plus 2300 divided by root 3, so this comes out to be 1732.1, and the top one 45.19 into 12 into 0.666 comes out to be minus 361.16. This divided by 1732.1 tan inverse. So delta comes out to be minus 11.78 degree. Okay. So this is the value of the delta. Okay. Negative, of course, it should be negative because the EF should lag the Vt. What is EF now? So EF, right, I can replace in this equation. So EF will be equals to minus IAXS minus IAXS, right? IA, this numerator only, okay, minus 45. So minus Ia dash into XS into cos theta dash divided by sine delta. So sine of delta into Ia dash is 45.19 into 12 into 0.666. Okay. So EF comes out to be 1769 352 volts. Okay, this is what my EF comes out to be. Now they're telling me that excitation is constant, I am changing the power. So power P double dash has changed to 60 kilowatts, right? So basically what is it equals to? It is equals to VT IA root 3 VT IA, sorry, not VT, sorry, root 3 into VL into IL into cos of theta double dash, IL dash into cos of theta double dash, right? So I know what is VL. So from here, right, I can get this information that IA double dash into cos theta double dash will be same. That will not change. Okay. IA double dash into cos theta double dash will be same. So 60,000 divided by root 3 into 2300 into 60 into 10 cube. So it is 15 basically. So IA double dash into cos theta double dash is 15. Okay. Now can I replace this? Can I use the same equation again? Yes. I can again use the same equation here, right? This will still satisfy. Remember, your EF will not change. EF still will be same. So here EF will be same. Your delta will change actually. This will become delta double dash. This will be delta double dash. This will be delta double dash. This will be IA double dash. This will be sin theta double dash. This will be cos theta double dash. IA double dash. Okay. So here, right, I can replace IA cos theta double dash. I know what is EF. I know what is XS. So I will be able to find out my sin delta dash. Sin delta double dash. So my sin delta double dash will be simply equals to IA double dash, or you could have done this formula, right? You know this formula, power is equals to EF VT by XS sin delta double dash. This also you could have used. So remember, this is single phase power, right? This formula also you can use. Anyways, so either you use this one, okay, or you use this one, both will work. Sin delta double dash will be minus of IA double dash, I don't know, but IA double dash cos theta double dash, I know it is 15.06. So it will be minus 15.06. XS, I know what is the value of XS. It is 12, right? XS is 12 basically. Divided by, that is EF, okay? So EF is equals to EF value we already know. EF excitation will be constant, that is 1769. Okay, am I doing everything here correctly? Just give me 1 second. Will IA, what was the IA previously? IA value was okay, it is fine only, yeah. It is fine, yeah. So 1769.352. So this into 12 divided by 0.352 sine inverse. So it is negative. So delta right now reduces. So your delta double dash is minus 5.86 degree. Okay. So your delta obviously will change. It will become minus 5.863 degrees. What have they asked? They have asked the new armature current and power factor, right? So now with this I can easily find out the armature current and power factor. How? So I can replace this delta dash in this equation. Here, right? I know what is VT, I know what is EF, I know what is cos delta dash. From here I can easily, okay, I can easily find out IA double dash sin theta dash. Okay, I can easily find out IA double dash sin theta dash. So what will be IA double dash sin theta double dash? It will be basically EF cos delta double dash minus VT divided by XS. Okay, so from here I can easily find out, I know what is my EF into cos of this, right? Cos of this will be hold on, cos of this into EF, that is 1769.352 minus VT. VT is 2300 divided by root 3 divided by XS. XS is 12. So this becomes 36.016. Okay, this is what my IA double dash sine theta dash is, theta double dash. So if I take the ratio of these two values, I will be able to find out tan theta double dash. So tan theta double dash will be what? This divided by IA cos theta double dash, that is this, right? So it will be 36.016 divided by 15.06, right? Because IA cos theta double dash we have already derived over here. So from here I can find out my tan theta double dash. So this divided by 15.06 tan inverse. So here theta double dash comes out to be 67.37. And one more thing, you have you have reduced the power, so it will be leading only, because what will happen if you have reduced the power, right? So remember, if you have reduced the power, right, where will the power factor graph shift? This cos theta. So power factor graph initially was here, now it has shifted to here. Okay, so you have reduced the power, so that basically previously with keeping the same excitation, if let's say it was nominal excitation, now it has become leading. So this has become leading. So your angle theta dash, theta double dash is coming positive. That is correct only, right? Because it should lead the voltage. Okay. So what is the new power factor? Cos theta double dash. So cos of this, right, will be 0.3866 lead. Okay. And what about the power? The power will be cos theta double dash divided, like IA cos theta double dash I know, right? Sorry, not the power. What will be the armature current? Armature current will be 15.06 divided by cos theta double dash, because IA cos theta double dash is already 15.06. So this divided by 3.086. This comes out to be 39.04 amperes. Okay, so these two are the answers basically. Please be careful, right? This question is very, very elegant and very, very good. Okay, this question is very, very elegant and very, very good. Please be careful, right? There were two steps. Initially, what we did, we increased the excitation to increase my armature current. Okay, with keeping the load constant. Then in the second phase, I kept my excitation constant and I reduced the load to 60 kilowatt. So there were two phases. Okay, there were two phases. So please don't solve it like this. Okay, I show you the wrong ones as well, so that you are able to understand where you can make a mistakes, Okay, now let's just end this discussion with just a bit of theoretical points. Okay, about isolated and infinite bus. Okay, so isolated bus we have already discussed. It is standalone, where I want to discuss about the variation of voltage, speed and field excitation with respect to isolated and infinite bus. So for a generator which is isolated, which is operating isolated operation, basically I have a generator here and synchronous reactance is there, and directly it is connected to load. There is no infinite bus, right? Infinite bus meaning the voltage, all those things can change, right? This is not an infinite bus, right? Voltage and power factor, all those things can change. Power factor will be constant. So here the power factor will be constant because it totally depends. A single load is connected, right? So power factor will be constant because the power factor depends on the load. So if I change the speed input of the prime mover of the generator, what will happen? If I change the speed, it will change the frequency basically. If I increase the speed, frequency will change. Okay. If I change the speed, frequency will change. So in case of a normal infinite bus, right, frequency has to be constant. But here if I change the speed, the frequency will change. So here, right, one more thing is, if I'm changing the prime mover input, I'm giving more power. I'm giving the generator more power input. So what will happen? Load can take a constant amount of power. It can only take constant amount of power. But in case of an infinite bus, what used to happen is, if I increase the prime mover, I can deliver more power because it's an infinite bus. It can it can absorb infinite amount of power, but here the power is constant. So here on this end, if I'm increasing the power, what is happening? Then the rotor will rotate at a higher speed. Then basically what will happen? The frequency will simply increase. The frequency will simply increase because the energy will increase, right? So energy is increasing, so something has to increase, either the frequency or the power, because power is constant, because load can only take certain amount of power, constant power. So the frequency will increase. Okay, so the generator speed will increase, which will increase the frequency. Okay, so as an increase in speed directly leads to an increase in generated frequency. Okay, so because F is equals to N into P by 120, that simple formula, so it will directly increase the frequency. So the synchronous reactance also will increase, right? Because XS is frequency dependent, XS is proportional to frequency, so synchronous reactance will increase. The internal induced EMF also will increase because EF is also proportional to flux and frequency. What will happen as the EMF will increase, so the current will try to increase, right? Because of course more voltage, more current, and your synchronous reactance is also increasing, right? So synchronous reactance is also increasing, so it will be like a feedback loop. So then what will happen? Then your like Vt, what will happen due to increase in current? What will happen? This drop, right? Drop Ia into excess drop will increase. So if this drop increases, again the Vt potential initially it will increase, then it will decrease. So I cannot comment exactly, cannot comment. Okay, so in case of an isolated load, I cannot comment what will happen. So basically there will be fluctuations. So you cannot comment in case of an isolated operation. Okay, there will be fluctuations. What will happen to the power factor? So power factor for an isolated system will be constant because it solely depends on the load, and a same load is connected, so it will be constant. Now if I am varying the field excitation, what will happen? So if I am varying the field excitation, basically I am increasing the IF current. If I am increasing the IF current, basically I am increasing the flux. If I am increasing the flux, then basically the EF will increase because EF is proportional to flux, right? So EF will increase. If I increase the EF, then the terminal voltage Vt will increase, because Vt is what? Vt is EF angle delta minus EF angle delta minus Ia J Ia into XS. So automatically if EF is increasing, Vt will also increase. Okay, and if armature current is assumed to be constant, so that will also change actually. What will happen to the reactive power? Reactive power also will increase because I am providing more excitation, so generator has more flux, so reactive power will try to increase, right? Reactive power will try to increase, but the load can only take a constant reactive power. So then what will happen? Then basically it will try to increase the reactive power, but it will not be able to increase the reactive power. Then basically the voltage difference will increase further. Why? Because the what will happen is initially EF will increase. Okay, then due to EF increasing, right, Ia Vt will increase. Then suddenly if Vt is increasing, due to EF increasing, right, Ia will increase. If Ia is increasing, this drop Ia into XS will increase, right? So initially Vt was increasing because EF was increasing, because Vt is equals to this, so EF increase, Vt increase, but then this drop is also increasing. So then what will happen? Your Vt will reduce. So again in this case you cannot comment, you need exact values. So in case of an isolated system, you cannot comment what will happen. Okay, but one thing you can comment, that your active power P and Q will be constant. In case of an isolated system, your active power and reactive power delivered will be constant. It has to be, because load is a single load, right? It cannot change. So active and reactive power supplied will be constant. So these things you have to keep in mind. So for an isolated system, you cannot directly comment. Now if I am connecting it to a infinite bus, now what will happen? Now if I change the prime mover input, okay, so of course I cannot change the speed and frequency because it is connected to a infinite bus. If I try to change the speed and frequency, if I try to change the speed and frequency, right, this is infinite bus. If I try to change the speed and frequency, what will happen? It will just not connect with the bus because this bus has constant frequency, right? It will not synchronize. So we will study, there is a chapter synchronizing. So it will basically not synchronize, right? So not possible. So we cannot change the speed and frequency, because speed and frequency both are same thing. I cannot change the speed and frequency. So when when connected to an infinite bus, the generator speed and frequency are fixed, dictated by the grid. We cannot change it independently. If I try to change it, it will go out of sync of the infinite bus. Okay, so we cannot do it. What we can do is we can change the prime mover input. If I change the prime mover input, what will happen? Basically, the active power, whatever it was delivering, will increase. So if the active power increases, keeping the excitation constant, Vt is also constant, what will change? Your delta will increase. So basically your load angle will increase. So it can go out of stability. Okay, we will discuss about this. So there is an increase in the input power which will shift the load angle relative to the stator field, enabling the generator to supply more power. Okay, so your load angle will increase. That much I can surely comment. Okay, impact on power factor. So impact on power factor, if I am increasing the power, right, what is happening? For a synchronous generator, the load curve, the power factor curve shift on the right hand side. So for the same excitation, let's say nominal excitation, this left hand side is leading, right? So, and this left hand side is leading. So previously if it was nominally excited, now it will be leading power factor. So it will be more leading. No. Actually this is wrong. This is wrong. The power factor will be more leading. If power is increased, it will be more lagging. If power is reduced. Okay, so either it will shift on the left hand side or the right hand side. So if power is reduced, it will be more lagging. If power is increased, it will be more leading, because the graph will shift on the right hand side. Okay, so this right I have to change. Yeah, now I hope there is no confusion. Now if I'm changing the field excitation, we have already discussed, right? If I'm changing the field excitation, what will happen to the active power? So the terminal voltage and frequency will remain constant, right? That is for sure. What will happen to the reactive power? If I'm changing the field excitation, that is I'm providing more flux, right? So the reactive power delivered will be increased. So it will deliver. If I'm increasing IF, that means it will deliver more reactive power. Okay, yeah, that is the conclusion. Basically, under excitation is less, so the generator will absorb reactive power. Over normal excitation, generator will not absorb any reactive power, and over excitation, generator will deliver. So basically you see that in all these cases, from under excitation to over excitation, the reactive power delivered is increasing, right? So that is what I have discussed. If I am increasing the field current, reactive power will be delivered. So that is what we plot in V curves. Okay, that is what is plotted in V curves. So I just wanted to quickly summarize this. Okay, so you can this synchronization and all these things we will discuss. Power factor correction will be discussed in the power system subject. Okay, and synchronization will discuss properly. We have to synchronize with the infinite bus, otherwise the generator will not work. Okay, so yeah, that's it basically for this question. Let us not see the similarities and dissimilarities, otherwise you will get confused. So yeah, that's it basically for this lecture. I will see you in the next lecture with a new topic, that is salient pole rotors. Thank you, and I hope you have enjoyed this lecture. I will see you in the next lecture. Until then, happy learning.